Hello, everyone. Welcome to my lecture. So this lecture is being recorded as part of the 2021 Sagan Summer Workshop. My name is Aline Vidotto. By the time I'm recording this talk, I'm an academic at Trinity College Dublin, but very likely by the time you're watching this talk, I'll be an academic at Leiden University. Now, the workshop organizers asked me to talk about how irradiation and stellar winds can affect the early evolution of planetary atmospheres. Before I move on to this topic, let me give you a very brief relevance of the theme. So why is atmosphere relevant? So we believe that in addition to have liquid water in the surface of a planet, an atmosphere can play a really important role in habitability for life to develop. The other thing that I find very interesting is that atmospheric laws can sculpt the mass radius distribution to the population of planets we observe. And I'm going to talk a little bit more about this in a few slides. But here, just a very quick illustration. We have the number of planets detected as a function of planetary radius. And you see this valley. This depletion of small planets has been associated to evaporation. So atmospheres are important, and the outline of this talk is the following. First one is, I would like to touch upon the question, how do we know the exoplanets are evaporating? And why do they evaporate? Then I'll talk about the evolution of how stellar radiation and winds will take place. And then finally, once we understand the second point, I will then move on to the third point, which is on the effects that the stellar wind and also the XUV will interact with the atmosphere and the effects they will play on escape. So the first question, how do we know that planets are evaporating? So there are two main views that exoplanets are evaporating. The first one is related to indirect observations. So what you have here is planetary radius as a function of irradiation. So this is the energy flux impinging on your planet. You see that there is a quite empty space here. This is known as the hot Neptune desert. So this desert is believed to be caused by evaporation. So planets maybe were born in this region, they evaporate and they move to lower parts of the diagram. The other indication that exoplanets are evaporating is given by this radius valley. Now you have to be very careful and pay attention to see this valley here. It is more easily perhaps to see if you plot them in the form of a histogram. So you're collapsing these in orbital periods. So you have here the number of planets per stars within this orbital period smaller than 100 days as a function of size. You see the valley here in the middle of these two peaks. Now, what we have is this peak here, which is around 2.5 for Earth radii, is formed of volatile rich planets. And this other peak here is at around 1.3 Earth radii, is formed of rocky cores. The interpretation is that this radius valley, these planets, they were born as big volatile rich planets, and with time they evaporate to such an extent, then they moved to this other peak here. So they became rocky cores. So evaporation in these two regions of the diagram, in the hot Neptune desert or in the radius valley, is therefore key to shape the radius mass distribution of exoplanets. This is the indirect way to infer evaporation on exoplanets. A more direct way is through transmission spectroscopy. Now, in this case, you are limited to a few objects. You can't do this in terms of a population, at least not yet. So what we have here is your star. So this is the stellar disk. This is the planet that is transiting. So the way you detect the atmosphere is simply put in the following recipe. So you first take a spectrum of your star, so planet is out of transit. Then you take another spectrum of the star when the planet is in transit. So when you divide the two spectrum, you find the percent of the absorption that is given by the planet atmosphere. So the idea here is that if you were to only measure broadband optical transit, you're going to be looking at the planet disk in front of your star. So you would have a light curve that would be represented by this brown curve. So this has a shallow transit. Now, if you look at the spectral lines, chemical elements that are present in the atmosphere of this planet, for example, here in Lyman alpha, in this example, you would see a transit light curve that is much deeper. So this technique is called transmission spectroscopy, because during transit, the light of the star is transmitted through the exoplanet atmosphere. Now you see that the shallow transit in the broadband optical light curve is nearly a square shape, but the Lyman alpha transit here has this funny shape. So it has an asymmetric, what we call an asymmetric transit. So it's not symmetric about mid-transit. And the reason is that your atmosphere can take different shapes. So if your atmosphere, for example, is elongated, you would see a longer egress time of your planet. And that's actually what has been seen, for example, in this in the transit of this worm Neptune. So GJ436b orbits an M dwarf. The optical light curve of this planet is shown by this really by this horizontal line. And if you look carefully, you're going to see that there is this very shallow or this small transit here. So this is the optical transit. Now, if you look at the Lyman alpha transit, you see this amazing absorption. So you end up absorbing about 60% of the stellar light in Lyman alpha line when the planet passes in front of the star. The interpretation of this dramatic absorption is that although the planet is very small, it is surrounded by an evaporating atmosphere that is occupying a very large volume. And not just occupying a large volume, but also having this really elongated tail, which is responsible for the egress being very slow. Lyman alpha is great because these planets, they are believed, these warm Neptunes, for example, are believed to be hydrogen rich. The problem is that for us to observe in Lyman alpha, you have to go to space. More recently, the community is also looking in the infrared light in the helium lines. So this is the helium triplet at 10 830 nanometers. Sorry, 10 830 angstrom. And what you have here is the light curve, is the line profile of WASP-69b. And you see here that there is a strong absorption at 10 830 angstrom. You also see this in WASP-107b. So in these cases, you have an observation done from the ground with Carmenes. And in this case, we have an observation done from space in the infrared with HST. And again, you see here the transit depth being increasing as you reach the 10 and 30, the line center. There is a small difference here. Here you're looking at transit depth, so the larger the transit, so this is why the curve goes up, and while here you're looking at the transit obscuration, so this is why the flux goes down. So you can think of converting one to the other by just taking one minus the value, okay? Now, the common feature where we observe evaporation in helium lines is that the star has to be relatively active. we need to have enough energy flux, and in particular, this energy flux must come from the EUV to lift the atmosphere. Now, I hope I have convinced you that you can observe atmospheric escape in two different ways, what I call the indirect way by measuring population, and in the direct way by measuring transmission spectroscopy, doing transmission spectroscopy of a specific planet. But now the question I would like to address is what are actually the physical causes that generate evaporation in these planets? Now, atmospheric losses come in different processes, and I have here this really nice sketch illustrating the diversity of processes in escape. And the core here, the key ingredients for escape are the stellar wind and the stellar energy flux. Now, depending on whether your planet has a magnetic field or not, you can have different channels of escape. Also, depending on whether your planet is terrestrial or a gas giant, you can have a different channel of escape. And this diagram from what I could get is the most complete one, but it's still, we have other processes not included here. And one process that I'm going to focus on this talk is on stellar wind stripping. So you're looking at the run pressure of the stellar wind that is eroding the atmosphere of the planet. In general, you can divide your loss processes into two types, a kinetic process and a fluid process. So kinetic means you have individual particles or ions or molecules that are escaping the atmosphere of your planet. For example, if you think of Jean's escape, where the molecules or the ions in the tail of the Maxwellian distribution have a higher velocity than the escape velocity of the planet. And if these atoms are moving upwards, they can eventually escape the exosphere of the planet. A fluid type of escape involves you driving not just a few particles out of the atmosphere, but you're driving a bulk outflow. So essentially you have the whole atmosphere moving outwards. We usually call a fluid process or a hydrodynamic process. They're equivalent, okay? So a simple assessment that I will suggest here is that if you have an inflated planet, meaning the planet has a low gravity, and if this planet is highly irradiated, either because your star is very active, is very young, or because your planet orbits very close to the star, then you generate a bulk outflow. That's a simple assessment. Because of these bulk outflows, they are actually important in closing or in a youngish planet. So you don't necessarily need to be too close to the star if the star is very young. So sometimes it's good to think about closing planets as proxies or conditions that will enable you to study a young planet that is a bit further out. So you can learn from one and apply this to another set of planets. Now, for these particular planets, there are two suggested avenues of evaporation. So you can, for example, think that this planet is being irradiated by the star, and this irradiation is helping to heat the atmosphere, and the atmosphere more easily expands and outflows. So this is an external driving. Or you can also think about an internal driving, say your planet is very young, is still contracting, so it is converting gravitational energy, is releasing gravitational energy, and therefore you are providing an internal source of heat to this planet. So let me focus on these two types of evaporation. So the first one, the photon evaporation. So imagine you have your planet and your planet has a hydrogen-rich atmosphere. So these are my hydrogen atoms. You have neutral hydrogen, you have ions as well. So imagine now your star is irradiating this planet, and this planet is receiving a bunch of XUV photons. So the relevance of XUV is that you need energies above 13.6 eV. So you need to go above the ionization threshold of hydrogen. So when your photon is absorbed by your hydrogen atom here, you will ionize, so you have your proton and your electron then separated. Now you use 13.6 eV of energy to ionize the atom, but there is an extra energy because remember the photons here, they all arrived above this energy threshold. And this excess energy is essentially converted into thermal motions. First order approximation, this excess energy becomes heat. Of course, you could use this excess energy to ionize further more or ionize other elements, but for now, first order approximation, this excess energy is converted into thermal motions. So the outcome of this process is that you increase the atmospheric temperature of your atmosphere. The other process that I mentioned, the one that uses internal energy. So you're looking here at a planet. So after formation, the planet is contracting. So it's releasing gravitational energy. And therefore, this energy is being used to heat the atmosphere of the planet from bottom to up. Now, notice that the outcome of these two processes is again an increase in atmospheric temperature. Now, I'm insisting here on the temperature because in fluid dynamics, in particular in the hydrodynamic scape of exoplanets, the temperature is really the key process or the key ingredient to drive the flow. Now, when you have high temperatures, you create a gradient of thermal pressure. So pressure is proportional to density times temperature. This gradient of thermal pressure is nothing more than a force. So this force is what is driving your flow. So I have here a sketch showing the three forces that we are considering in this case. So here is the momentum equation. So this is mass times acceleration is equal to the sum of the forces. Okay, so the forces that I'm considering is gravitational force from the planet. So this force points down. Tidal forces, so if you have your star here, your star is trying to pull material from the planet towards it, so it's attracting gravitationally attracting some of this material, and also the thermal forces that I mentioned just here. So first thing for you to notice is that the mass here is not really a mass. So in fluid dynamics, the mass is replaced by density, which means that all the forces that I'm writing here, they are not actually forces given in newtons or in dynes, they are forces per unit volume. So these are newtons per cubic meter or dynes per cubic centimeter. So let's rewrite this equation here, putting the correct expressions for each term. So the acceleration in steady state of a fluid, you can write it as u times du dr. Okay, so this is the acceleration term. Then the gravity of the planet has a minus here because the force is pointing towards the planet. Now we have here the tidal forces. So these are the forces of essentially the star affecting your atmosphere. Now you think that if the star has a higher mass, the larger is the tidal forces, so it attracts more material from the planet. Or if your orbital distance is small, the planet is closer to the star, then of course this force is going to be larger. And the thermal force. Now there is a minus here, but I just would like to remind you that the pressure is higher at the surface and lower as you go up in the atmosphere. So dpdr actually is negative. So the minus here means that the thermal forces is actually positive and helps to drive flow out. You can look at the derivation of this equation in section 5.2.a of my review. So this is free access for you. This equation is actually used in stellar winds. So that's actually an equation that we borrowed from the stellar wind theory, and we have used it in exoplanet evaporations in the hydrodynamic process. Now, one thing to keep in mind here is that the momentum equation does not care what is causing the gradient of the pressure. It doesn't care if it's a heating coming from the core, if it's stellar photoionization, or if it's something else completely, or if it's actually a combination of these two processes. All it cares is the gradient of the pressure. It cares about the gradient of the pressure. So the distinction actually, when we talk about different processes of escape, it will enter mostly in the energy equation, which I'm not presenting here today. But what I would like to show next is a limit that we have used, we have encountered many times in the literature, called the energy limit escape. Now, this is essentially a particular limit of hydrodynamic escape, and it's very good, it's very cool to use it because we have a simple analytical expression for that. And I'm going to derive this now. So if you're thinking of an energy limit, you're essentially saying that the irradiation that is arriving at your planet is actually being used to drive the outflow. So you are converting the input energy from irradiation to kinetic energy. So let me show you this diagram. You have your star, you have your planet. Now your planet still has this funny atmosphere, but when the planet is essentially absorbing the photons from the star, it has an effective radius. Okay, so this is what I call the effective size of the planet. So there is a cross section. So a fraction of this energy flux is intercepted by the planet. So when I write the energy input, I have epsilon times the flux times the cross section of the planet. Now, this is what is driving the flow. So the flow is then the kinetic energy of the flow is the mass times the squared velocity. Now, here, U term is the terminal speed of the escaping atmosphere, okay? And because this equation here is if you do the dimensional analysis, you have here an erg per second. Here we have m dot, so this is evaporation rate, so it's mass per second, okay? So here, for example, grams per second in CGS units. Now, notice that I use here a fraction, epsilon. So we are now here playing safe. We're saying that it's only a fraction of this energy that is actually going to be used to generate the outflow. Remember, part of this energy might be used to ionize the atoms in the atmosphere, so it's not 100% of the energy that is going to be used to drive the flow. Now, the things that we have to, the terminal velocity is the property of the flow that we can only derive if we actually solve the momentum equation I showed you before. But for simplicity, in the energy limit escape, we are going to have a second assumption. So the first assumption is that the energy balance. And the second assumption is that the terminal velocity is actually the same, on the same order as the escape velocity of the particles when they are at the surface of the planet. So this is square root of 2gm over r, and here the p indicates the planet, okay? So mass of the planet and radius of the planet. Now, if I plug Vesc here and replace U term by Vesc, you can then rearrange this equation, and I have the mass loss rate or the evaporation rate by energy limit in the condition of the energy limit escape that is given by this ratio. Okay, so this is how we derive the escape rate in the energy limit approximation. Now let me just rewrite this equation. So this is the energy flux at a distance a, at the orbital distance, which is also the luminosity of the star divided by 4 pi a squared. So you can rewrite this FUV, and you can rewrite this equation here as LUV divided by a squared, and then you cancel a pi in this process. The other thing you can do, you can rewrite this equation using the average density of the planet, which is the mass divided by the volume, assuming a spherical volume. Now, I'm going I kept the effective radius here, but for simplicity, I'm going to replace this effective radius by the radius of the planet, so which is not that bad approximation. And then you end up with an R planet here that goes to the numerator. You end up with an R cube, and then you can rewrite this with a density in the denominator. So these equations, they are all equivalent, just written in different forms. And the reason why I wanted to write this equation this way is because now we can qualitatively assess what is important and when it's this escape important. So evaporation rate is larger if your planet is orbiting at close distances. So if you have a small a is in the denominator, then m dot goes up. It's also important where the density of the planet is smaller. So if you have an average density here, for example, a gas giant that is smaller because the density is in the denominator, m dot also goes up. And also it is bigger, m dot is bigger when the luminosity of the star is larger. And usually these luminosities are larger when the star is young. And therefore escape is a very important process in younger photo evaporation process is very important in young systems. Now, putting together these 3 bullet points, we can conclude that this form of hydrodynamic escape is important in planets closer to the stars, so hot Jupiters, warm Neptunes, and also planets orbiting younger stars. So I have here a diagram looking at the estimates of mass loss of evaporation rate for about 400 exoplanets, all orbiting stars about the size of the sun. And what you're looking here is the potential energy of the planet per unit mass and the stellar energy rate that is deposited at the planet. So you look at, this is essentially the numerator and the denominator of the m dot equation I showed 2 slides ago. And color-coded is the escape rate. So everything here is given in log. So escape rates range from 10 to the 4 to 10 to 16. So the higher the energy that is the planet is receiving, the higher the mass loss, and also the lower the potential energy of the planet, also the higher the mass loss. Notice that the energy here is the axis is swapped, so higher energy is on the left. To give us an idea of the amount of escape, we are actually ranging between here 10 to the 4 to 10 to 14 more or less, okay, grams per second. Now, this is this concludes my initial introduction on whether we observe escape in exoplanets and also on why these planets are evaporating. I now would like to move on to the second part of this talk, which is on the evolution of stellar radiation and winds. So I have been asked to talk mostly on on how stellar irradiation and stellar wind erosion can shape atmospheric evaporation. Therefore, I will concentrate on the process of photon evaporation. So let me just move on now very briefly and talk about winds. So stellar winds are very relevant, very important in the life of a low mass star. The reason is that the stellar wind can remove angular momentum from the star. Therefore, the star spins down with age. And when the rotation rate of the star is reduced, you can actually change the angular momentum transport inside the star. So you change interior properties. And if you change interior properties, you change how magnetic fields are generated inside the star, and therefore you change the activity and the magnetism you see at the surface of the star. With a different magnetic field, you have a different stellar wind and the process and the loops close, okay? So this is what happens in the life of a cool, mostly a cool main sequence, the star, okay? So when the star is younger, actually disks and contraction are also important for the rotational evolution of the star. I'll come back to this point in a bit. But what we have to keep in mind is that the stellar wind is important for rotation, important for activity, and of course it affects detection of exoplanets and affects how we measure ages of stars and planets and so on. Now the question is, how do the winds, the activity, and the planets evolve with time? So unfortunately, we don't know much about stellar winds of low mass stars. It's very difficult to observe them. There is a bunch of methods that have been used and proposed to measure stellar winds in cool stars. And I have here a compilation of the results from different techniques. You have here the mass loss rate of the stellar wind as a function of X-ray flux. So this is given per surface area of the star, and it's all relative to sun. So the sun here will be 1, okay? So this is going to be 10 to minus 2, the value of the sun, and so on and so forth. Now, X-ray fluxes this is the flux at the surface of the star. So when the star is younger, it has a higher X-ray flux. So you're essentially looking at a time axis running from right to left in this plot. And the questions that are still open is, if you want to understand why we are here, we also want to understand how the solar wind evolved in this past 4 billion years. We want to understand what was the implication for a strong wind, apparently, in the formation and in the young solar system, and also in young exoplanetary systems. And then finally, we want to understand how the stellar wind can affect the exoplanet, not only the atmosphere, but maybe if your planet has a magnetic field, you also want to go to understand how it affects the magnetosphere of the planet. Let me show now, let me focus a little bit now on the activity. So activity and rotation are intrinsic, so they are intrinsically related. So let me show you first the rotation evolution. So you have your rotation rate, again in units of solar rotation rate, as a function of age. And each of these points, they are observations of clusters, and clusters are really good because we can have precise ages. So we go from 1 million year to 10,000 million years, so 10 giga years. Now let me show you a bunch of lines. These lines are models. So in a certain cluster, you have a number a variation or a range of rotation rates going from slow rotators to fast rotators. So you see here the green and the blue points, they are essentially the 25th percentile and I think 75th percentile, I'm not sure, but we are going to call them slow and fast rotators. So they are the envelopes of this distribution. The sun is shown here, and this is the old disk. So the galaxy, the stars in the old disk. Now, first thing to recognize is that when the star has an accretion disk, the rotation is regulated by this accretion disk. So the disk does not let the star spin up. It actually forces your star to keep at the same rotation rate. So it doesn't matter, the star is contracting, there might be winds coming out of your star, but the disk is locking the star in its rotation. Now, when the disk dissipates, and depending on whether the star is a slow rotator or a fast rotator, the disk dissipation time can be different. So after the disk dissipates, the star is free to continue to spin down, to contract. And conservation of angular momentum tells us that the smaller the radius of the star, the larger the omega. So the rotation rate goes up. And this is more or less where the contraction ends, and the star starts to enter in the main sequence, and then it evolves and it spins down because of the winds carrying away angular momentum. Now, we don't observe UV flux, so X-ray and UV fluxes, or it's difficult to observe them. So what these authors did, they actually used the rotation as a proxy to infer the X-ray luminosity and the UV luminosity of stars. And we can do that because of the link I just mentioned in a couple of slides ago, that stellar rotation is going to decrease with age. And it's also, and because the stellar rotation is linked to stellar activity also decreases with age. So we have actually here a closed loop, a feedback loop. Now, the fast and the slow envelopes in the rotation diagram is shown here as well. So the blue and the red curves. Now you see here that when the stars are young, they actually, doesn't matter whether they are fast or slow rotators, they have really high luminosity. So we are looking here in X-ray from 10 to nearly 10 to 31, and here actually above 10 to 31 in the EUV. And with time, this activity decreases. Now, we are interested in this lecture on younger ages. Now, you see here that up to 100 million years, the X-UV fluxes of these stars, they can be substantially large. And this is important because it affects the evaporation of a planet. Now, what these authors did, they placed a planet at 1 AU, so it's not a closing planet here. It's a planet, a terrestrial planet that has an initial atmospheric mass that is about 0.5% of the mass of the planet. So they placed this planet at 1 AU, and they studied how much evaporation this planet would undergo as it evolved. So depending on whether the planet is orbiting a fast or a slowly rotating star, the outcome of the evaporation can be very different. So if the planet is orbiting a slowly rotating star, about 45% of its initial atmosphere will remain. So there is, the planet loses 55% of the atmosphere, so it's a strong, a significant loss, but still the planet retains some atmosphere. Now, if your planet was orbiting around a rapidly rotating star, the outcome is very dramatic. The atmosphere is entirely lost within 100 million years. So this first 100 million years, they can be very important for the evolution of the atmosphere. And as I said before, this planet is not a closing planet, it's a planet orbiting further out. The other thing that we learned is that escape can affect the internal structure of the planet. And I have here the evolution of the radius of the planet as a function of age. Now this is given in years, so this is 10 million years, 100 and 1 giga-year. And what you're seeing here is the evolution happening without escape. So this is essentially the internal structure readjusting itself as the planet evolves with time, no escape included. This is what happens to your planet if you assume the planet is losing mass and you're using the energy limit approximation. And finally, this is what happens to your planet if you're actually including a more robust model for evaporation using hydrodynamic escape. Now, the takeaway message here is that yes, evaporation is important for the internal structure of the planet. And in particular, hydrodynamic, you see quite a significant change here in using energy limit or hydrodynamic prescriptions. Now, the first thing is that I told you how to derive the energy limit equation, because you can do like a quick estimate by yourself. But say you don't want to use the energy limit, but you also don't have a hydrodynamic code to calculate your escape, then I have here listed here two free tools provided by Daria Kubishkina. And the first tool here is essentially a Python interpolator. So you give the properties of your planet, and this interpolator will use a grid of hydrodynamic models that have been already computed, and will give you the evaporation rate. So you can plug this number in your proposal or in your favorite code. The other advertisement here is this evolution model here was produced by Daria Kubishkina, and she was using MESA. So MESA is a stellar evolution code, and she's using this code and adapting it to incorporate hydrodynamic escape. And if you want to run your own model, MESA is publicly available, and the inlist, so the input that you need to create your MESA run, is actually available in this link. Now, I showed you the evaporation, or the importance of evaporation at early ages for a planet that is orbiting further out. And I also want to show the evaporation levels for a planet that is orbiting close in. So this is a planet at more or less 0.05 astronomical units. So this would be a closing gas giant. And again, you have here the planet orbiting a fast or a slow star, a slowly rotating star. And this is important because the level of fluxes the planet will receive is going to be different. Now you see here that if this particular planet, the first 100 million years, the evaporation is super large. So it's 10 to 13, 10 to 12 grams per second. And mostly this contributes to a lot of mass being evaporated. So the estimates in this model was that 20% of the mass was lost through evolution. Now, the cool thing about a hydrodynamic model is that you can obtain the velocity and the density of your escaping atmosphere. And if you know that, if you know this structure, you can actually predict the observational signatures that you would get if you were to observe the system. So in this work, we looked at the Lyman alpha line and the H alpha line. Now the color here indicates age. So the darker the color, we have a younger star. So this is 10 to 1 million year, and this is 10 to 4 nearly million years. So about 10 giga years. And what you see here in the Lyman alpha line, you see this is the transit depth at mid-transit. You see that the line is broader at younger ages because the speed of this outflowing atmosphere is actually larger. And the line is also very saturated, the line center. In H alpha, you see transits that have an excess of the geometric transit of about 3 to 4%. Now, the younger the star, the larger is this H alpha signature. The problem is that the younger the star is, H alpha is also coming from the star is also stronger. So you start adding a lot of background noise in your transit, so it becomes more difficult for you to disentangle whether the signature or the absorption you're seeing as the planet moves across the stellar disk is coming from the absorption of the planet, or is actually coming from the background, so the variability of your star. But the thing I would like to highlight here is that these line profiles, they are symmetric. And we know that in reality, line profiles are not symmetric when you look at transmission spectroscopy studies. And the reason is that these models here, up to now, they lacked the stellar wind interactions. And that's what I would like to discuss now in this last part of my lecture. How stellar wind interacting with the atmosphere of the planets will shape and will affect these line profiles. Again, here you have your planet, you have X-ray, and you have UV irradiation arriving at this atmosphere, and you also have stellar winds. Now, let me show you a movie to illustrate what I was talking before about stellar wind stripping. So what you have here is a planet. So what you have around the planet is the atmosphere of the planet. So it's this escaping atmosphere, okay? And the color code is the density, mass density. So your star is not shown in this movie. It's actually coming from the left. And the stellar wind is going, as soon as I start this movie, you're going to see the stellar wind being injected from the left boundary, and it's moving inwards the grid of the simulation. This is a 3D simulation, but just for illustration, I have here shown in the orbital plane. Now, the simulation is done in the reference frame of the planet. So the planet is going to sit still when the movie is played. And just so you know, the orbital motion is pointing up, okay? And here is, you see already that there is a different shape or a different density distribution in the night side. And this is because of the planet's shadow. We're looking at the night side. Okay, so let me play the movie. You see here that when the stellar wind started interacting with this planet, we created this tail of material. So essentially this tail, it is formed by the interaction with the stellar wind and also created by the motion, the orbital motion of the planet. The other thing you see is that there is a bow shock that is created. This is because in this system, we have this is because in this system, we have supersonic velocities. And therefore, the interaction happens at supersonic velocities, you form a bow shock. Now, this is the stellar wind stripping. The thing and the difficulty and what makes this so exciting is that the stellar wind actually has different effects on the atmosphere. And just to illustrate, we already talked about stellar wind stripping, so also more commonly known as erosion of the atmosphere. But the stellar wind could also create an atmosphere. This is a suggestion that we proposed a couple of years ago for this rocky planet. Of course, the stellar wind could do nothing. Maybe you have a very weak wind. This is not as an exciting case. And the recent proposal that I suggested was that the stellar wind could actually prevent escape. And I'm going to focus on this because I think this is relevant for young systems. So let me draw you a sketch. You have your planet, you have your atmosphere in the two cases. You have the stellar wind coming from above. So you have this interface between the stellar wind and the planet. Now, when the atmosphere of the planet starts to evaporate, it acquires velocity as it goes up. And eventually, it crosses what we call the sonic radius. So the atmosphere is subsonic here and supersonic above this radius. Now, when the atmosphere of the planet is supersonic at the point where it interacts with the stellar wind, you cannot transmit information back to the planet. So the stellar wind shapes the atmosphere, so it creates this tail, it affects the transit signature, but not necessarily, it does not change the amount of atmosphere that is escaping. It's almost like the planet cannot hear the information that the stellar wind is shouting towards it. Now, in this scenario, either because your stellar wind is stronger, which is very likely to be the case when you're young, or because the atmosphere of the planet is, the escape is weaker, the interface between the two, the stellar wind and the outflow of the planet happens at subsonic velocity. Now, in this case, the information that the stellar wind is shouting to the planet can be heard. So the stellar wind is saying, stop sending mass, and then the planet stops or reduces the amount of mass it is evaporating. So the The suggestion I presented a couple of years ago is that stellar winds can reduce or could even suppress mass loss from their exoplanets. And what we did here was a study varying the gravity of the planet, the orbital distance, and this is actually the UV flux. So you have a star here, the star is at 4.6 gigayears. I studied also other stars that are younger. But the line that I would like to highlight is the line in pink. Oh, by the way, the evaporation rate is given in color code. So the line I would like to highlight is this one in pink. And what you see here is that planets that have that fall in this physical, in this region of physical parameters, they actually are in the non-confined scenario. So the planetary outflow is supersonic when it interacts with the stellar wind. On the other hand, the planets that fall in this other scenario, they are what I call confined. So they are the planets that the mass loss rate we estimate here might actually not be correct. So the mass loss rates were estimated using 1D hydrodynamic models. So models that do not consider the effects of the stellar wind can actually overpredict atmospheric escape in exoplanets. And including, when I say models, I actually include my own model that I used in this diagram. And it's interesting that by the time we were submitting this paper, there was the announcement that Pi C was expected to show a very strong evaporation, but none was detected. So we suggested, could it be that this is confined by the stellar wind? Of course, it's not the only alternative, but it's an alternative we suggested. Now, in this work, we were using a 1D radiation hydrodynamic simulation. But when you are doing 1D simulations, there is no way you can include stellar winds. So we started looking now at a 3D simulation. So we are going to look at the simulation in particular of this planet here, this hot Jupiter. And I'm showing you here the equatorial plane. So the stellar wind is being injected in this scenario from below. You have the planet. The streamlines in black are velocity streamlines of the outflowing material from the planet, and the gray streamlines are the streamlines of the stellar wind material. And here color-coded we see the density. So the sonic surface is shown by this gray iso contour. Now, what we wanted to study is to see whether if you were going to increase the mass loss rate of the stellar wind, we would actually stop or we would prevent escape from the planet. Now, I have here 3 different scenarios. And in the first scenario, the planet is here in the center, the stellar wind is coming from the left, and the mass loss rate of the stellar wind is twice that of the sun. As you move to the second plot panel, you have a mass loss rate that is 10 times of the solar wind and finally 20 times of the solar wind. So you see here the sonic surface of the atmosphere of the planet is this circle here at the center. So when you increase the stellar wind mass loss rate, you see that the sonic surface is undisturbed in this scenario, and it starts to be connected to the surface from the stellar wind itself until you get a completely what we called an open or a disrupted sonic surface. So this surface is here actually delineating the shock of the material. Now, the conclusion here is that the stronger the stellar wind, you first cause your atmosphere to occupy a lower volume, and second, you open this sonic surface. To investigate whether this changed the evaporation rate of the planet, we calculated the escape rate. So we have here escape rate as a function of absorption. So we are looking here at the amount of absorption in Lyman alpha line. But in reality, the first point here assumes that this scenario, this simulation did not have a stellar wind. Then we increase the stellar wind by a factor twice the value of the sun, and you kept increasing the value of the solar wind until we reached 100 times the solar value. So as you increase the stellar wind mass loss rate, the first thing was that nothing happened to the evaporation. So it remained at the original value where there was no wind. But eventually, when you started disrupting the sonic surface of the planet, you started decreasing the escape rate. Now, the decrease is not really big. If you look here, we are at 2, 3, 4, 5. We are at between 5 and 6 times 10 to 11. And here in the most dramatic scenario, we are about 2, 10 to 11. So the amount of evaporation was not actually dramatic in the system, but the absorption that we would detect was actually dramatic. No, so here we would have about 20% of absorption, and here you would have only 5%. So the observational signatures are strongly affected by the presence of stellar wind, even in the scenario where the stellar wind is not affecting the escape rate. And this is because the stellar wind shapes the structure of your escaping atmosphere. Now we come to this very relevant case of a young system. So you have here Eumic B. So this is a young Neptune-sized planet orbiting a 22 million year old star. So this is a pre-main sequence M dwarf. This was published last year and by Peter Blabschen. And we are now in this situation where, because the star is young, you expect this star to have a very strong high EUV flux. Therefore, the planet should evaporate a lot. But on this other hand, this star has also a very strong stellar wind, and estimates indicate something between 10 to 1,000 times the value of the solar wind mass loss rate. And you could have this stellar wind preventing or reducing the evaporation. So we run simulations to investigate that. And I have here just the scenario where the wind is 10 times or 1,000 times the value of the sun, of the solar wind. Again, I show density here in the equatorial plane. And you see that from left to right, evaporation rate was reduced by about 50%, so not super significant. But when you look at the Lyman alpha absorption, either in the blue or in the red wings, as a function of stellar wind mass loss rate, you see that the stellar wind can actually erase the signature of your planet just because it forces this atmosphere to occupy a volume that is small. And also, depending on how strong it is, this tail might be so directed towards the line of sight, the line of connecting the planet and the star, and the planet and the observer, that you might not be able to see much of the absorption. So you see here a very strong decrease in the absorption that we predicted. Another that we predicted. So another scenario that I would like to finish this lecture talking about is the case of planets that orbit active stars. So stars that are active, they are usually flaring. Sometimes these flares, they can be associated to coronal mass ejections, such as the one that I show here. Sorry, this is the movie of a flare interacting with a planet, and this flare causes the evaporation to increase. Now, in this particular hot Jupiter, we are looking at the light curve of the system at a particular date, April 2010, and then in September 2011, you look at the light curve of the system again, and you see this very strong evaporation. Now, what was a coincidence, or maybe not a coincidence, was that the star had flared 8 hours prior to the transit. So the indication is that the flare maybe somehow caused the planet to evaporate more. So there are some possible scenarios here. So one scenario is that the stellar wind changed when the CME, the coronal mass ejection path, propagated through the stellar wind. The other, and because of this changing stellar wind properties, it affected the evaporation of the planet. And on the other hand, what could have happened is that the flare adds as energy input in the atmosphere of the planet. Therefore, you increase the amount of evaporation. Or it could be both. To study this, we run a number of simulations, and I have here the 4 cases we studied. So the first case is what I call the quiescent case. So you have a planet. This planet is being irradiated by the star, but this irradiation is quiescent, so it's in a time where the star is not very active. There is also stellar wind interacting with the star, but again, not a very strong wind. Then you have a case B, where case 2, where the star has a flare and the radiation of the flare reaches your planet. Maybe there is associated CME with this flare, but this CME is outside the path of the planet, so it never interacts with the planet. A third case happens, for example, if the CME is directly directed to the planet, but maybe the planet did not see the flare. So this is a bit less likely scenario to explain the observations I showed you before, because we saw the flare 8 hours prior to the transit, but we have it here for completeness. And then in the fourth case, we have a CME and a flare interacting with the planet. Now, in this case, we have the strongest the most dramatic situation, let's put it like that. So what we did here, we investigated how the atmosphere of the planet would respond to these 4 situations. And what I'm showing you here is the density in the orbital plane of the planet. Again, the star is situated somewhere on our left-hand side. So first case is here, second case with flare, third case with CME, and fourth case with CME and the flare. So what we have here is what you see, the difference in the planet atmosphere is that when you have the normal or the quiescent stellar wind, the tail is oriented, is more tilted, and when you have a CME, this tail is more along. It shifts a little bit, and it's closer to the line connecting the planet and the observer, which is somewhere on the right hand side of this plot. You also see that the stellar wind we started with is actually significantly strong, because you already see the shocked material very close to the planet. So we are already in a very, very strong scenario. And when you have the CME, scenario is even more dramatic. Now, we wanted to see how the evaporation was changing. And I have here in this plot the evaporation rate for these 4 scenarios. And I also added here the no wind for completeness. And you see here, there is evaporation rate is on the order of, I don't know, something like 6 or 7, 10 to the 10 grams per second. And as when you have the CME, this goes up by more than an order of magnitude. So the flare alone did not change much the evaporation compared to the quiescent stellar wind, but the CME's effect were more effective at removing planetary material. Now, we wanted to compare this with observations. So data here is from the paper by Vincent Bourrier, 2013. And I have here in colors the different cases. You see here that if you look at the signature in the whole Lyman alpha line, the 4 models we have, they can actually fit the observation really well. So we need to look at a different thing, at a different property to disentangle which model is best. And we do that by looking at the blue wing of the line. This observation showed that the evaporation of the planet added to the absorption in high velocities, in velocities around 200 kilometers per second or so. So these are the material that is being blue shifted towards the observer. So if you only look at the signature in the blue wing of the line, you don't, you see indeed that the CMEs have either the case with only CME or the case with CME and flare, they have a larger absorption, but they don't yet match the value of that the observers derived. So there is still some work to be done in our model. One possibility is that these models that I just showed you, they were not including magnetic fields. So that's something that my group is currently studying. So I hope that in the next year or so, I'll have more to discuss on that. So let me conclude this talk with 4 key points. Atmospheric scape and the evolution of the planet depends on the history of the high energy flux of your star. The stellar wind is important in the evaporation of the planet. As I said before, in the very least scenario, in the most simple scenario, it can serve to shape the outflow of the planet. So it affects or erases, how I put it here, the signatures of Lyman alpha transit, in particular in young systems. But it can also so in the simplistic case, it affects the transit signature, but it can also affect the dynamics of the atmosphere. For example, I suggested that the stellar wind could help reduce the evaporation when the mass loss rate is really strong. But I also showed you in some scenarios where the strong stellar wind was actually stripping the atmosphere. So there is still some work to be done on why these 2 points, they might be, initially they can sound like they might sound like they go one against the other, but if we still have some work to do to understand where one case dominates over the other. So it might be that we are in very different parameter space, and we have to look more carefully in these 2 situations. So I hope we have more to bring to the community in the next few years as well. And then finally, in this last bit, I also discussed the effects of coronal mass ejections, which are believed to be more frequent the younger the star is. And I demonstrated that these CMEs and also the flares, they can affect the evaporation of the planet, but this can happen momentarily. And we believe that after the CME has passed, the atmosphere will readjust and maybe come back to the original rate that it had before the CME. It has been a pleasure to prepare this lecture. I hope this was of use to you, and you can connect with me here on Twitter, or you also have my email from the organization of the workshop. That's it. Thanks, everyone.